Hey there, I hope everything is going well in your world today. What we're going to be taking a look at in this lesson that I'm recording is going to be how we're going to find the cross-sectional volume of, some shape that we would have on our uh, coordinate grid or something like that, where we will have to use some kind of an integration process, either with respect to x, if we're going to be looking at maybe a vertical cross section, or something with respect to y if we're going to be doing a horizontal cross section. And that's kind of illustrated here in the text at the bottom. Of course, there's going to be generic shapes that we're going to be looking for the cross-sectional areas, squares, triangles, semicircles, things like that. We will look at some triangles a little bit differently maybe than you would have in geometry. But here, where am I looking at? If the cross-sections are perpendicular to the x-axis, we solve your equation in terms of y, like you're used to doing. But if the cross-sectional areas are going to be perpendicular to the y-axis, meaning that we have some kind of horizontal cross-section, we have to solve our equations in terms of x instead of y. Okay, and this is kind of what we would be looking at, where a of x or a of y may represent an expression that would be the area of your figure, whatever it happens to be. So let me get out of here. Let's go moving on. The area of a square, depending on what maybe the dimensions you might be given in a problem or what you remember seeing from geometry. A lot of times I'm used to just thinking of a square as a side, which, one of the characteristics of a square is that all four sides are the same. Any quadrilateral parallelogram like this, we can say the area is going to be the base times the height. So in this case, the area would be side times side, or side squared, not really anything new. Now with an equilateral triangle, we're going to need to remember that we have some properties of 30, 60, 90 triangles associated with it. If I bisect a 30, 60, 90 triangle from, or like an angle bisector here, so this is 30 degrees, this is 30 degrees, well, whatever this is, because it's equilateral, we'll say that this is a side, this would be the same side. Well, that means that from here to here, it would be half of that, and from here to here, it would be half of that as well, because the angle bisector from a vertex will bisect the opposite side of the triangle. So using properties of 30, 60, 90 triangles, if this is the side and that's the half of the side, then the altitude of the triangle that makes up the angle bisector, or the perpendicular bisector, if you think about it like that, from respect to the side there, that is going to be the short leg multiplied by the square root of 3. So we wind up here with the, and I'm not sure if I can really squeeze it in here. Let's just kind of make sure we can see it. That altitude is going to be the square root of 3 over 2, and I forgot to put an s here. So that would be the square root of 3 over 2 times the side, or s square root of 3 over 2. However you want to think of that to represent the height. So the area of a triangle, being what it is, 1/2 times the base times the height, here in this case, the base of the triangle, even if we think about it in terms of, half an s here and half an s there, it's still going to be one whole side, whatever the side length is. So here we're going to say 1/2 times the side, and the height in this case is going to be the side times the square root of 3 over 2. So when we simplify this, the sides in the numerator, side times side, will give me side squared radical 3, and in the denominator, 2 times 2 gives me a 4. So that's how I can kind of represent the area of an equilateral triangle. Take the length of the side squared, multiply it by the square root of 3, and then whatever that product is, divide it by 4. And these are the areas that we're going to be using. These are going to be things that we can use to perform integrations with. Here, in this case, we have a right isosceles triangle, and we're actually going to look at the right isosceles triangle in two different ways. Remember, right isosceles, that's going to be your 45, 45, 90 triangle. So again, special right triangle rules will apply. Again, just because we don't have anything else to call it, we'll just say that this is a side, this is a side. So according to the 45, 45, 90 triangle rules, the hypotenuse is going to be the length of the side multiplied by the square root of 2. So I say S radical 2 for the length of the hypotenuse. And if again, if I want to do the area of this right isosceles triangle, we're going to say 1/2 times the base times the height again. In this case, the base and the height would both represent the side lengths, or the two legs, I should say. So we're going to say side times side, which would result in side squared over 2. Now, the next one here that we're going to be looking at, this is a diagram that you may need to add into your notes, where it says isosceles right triangle with hypotenuse as, and this, I don't like this word, this should be base. Okay? Now, and that's why this side is labeled, that's why the hypotenuse of the triangle that you see is labeled B. Essentially what we're going to do is we're going to divide the 45, 45, 90 triangle into two smaller 45, 45, 90 triangles, where from here to here, this is going to be 1/2 of the base. Same thing here, this would be 1/2 of the base, whatever we want to call those. Well, essentially what we're doing is we're bisecting a 45, 90, 45, 45, 90 triangle. So this is 45, this is 40, 45, this is 45, this is 45. So essentially by bisecting, by putting in that angle bisector at the right angle, we're creating essentially two smaller 45, 45, 90 triangles, where we can think of the height here, because it's all for right isosceles, that is also going to be 1/2 of whatever the base of the overall bigger triangle is, or half of the length of the hypotenuse in this case. So if I look at this using area of a triangle rule again, area is equal to 1/2 times the base times the height. In this case, we're going to say 1/2. Well, the base of the triangle that we're looking at is just the overall hypotenuse, which is the base. The height of the triangle is going to be half of the base. So 1/2 of the base. So that will give us base squared over 4, or 1/4 base squared, however you prefer to think of it. And a semicircle, again, here, without, and there's nothing in particular saying that, what this is, but we typically think of this as the diameter. So the radius would be half of that. So from here, this way, that's a radius. From here, this way, that's a radius. A lot of times we think of the circle area in terms of the radius, because that's what it uses. And the area of a circle is pi r squared, so the area of a semicircle is going to be half pi r squared. And without understanding what we might have for r, there's really not much else we could substitute into it. We could write it, I guess, as pi square, or pi times r squared over 2, like that if you want. There's really not much more. I know some people, depending on what they want to use for the variable that they might have for a radius, they might be able to play around with the formula a little bit for the area of a certain semicircle, but essentially that's all we really need to have. Now what we're going to be doing is we're going to be taking these generic shapes, and the only basic geometric shape that wasn't really represented here. It was just maybe the area of a rectangle, but that would just be base times height, depending on whatever the base and the height are. Um, this is what they would look like if we were to kind of slice them up. Okay, again, cross section. Imagine taking an orange and slicing it in half with a knife, and when you peel the two parts apart, the circle that you see looking at where the flesh of the fruit is and the rind makes a circle. You know, presuming that your apple or your orange is generally sphere-like. Okay, that's just what the cross section is. And what we do is if we slice it up into an infinite number of cross-sectional areas, that will ultimately lead to the volume of a figure by those cross-sectional areas. And that's where we're getting into the idea of doing integration to get the volume. It's just very similar to what we did for area under a curve. We just took the sum of the infinite number of rectangles underneath a curve. Well, here we're taking the sum of an infinite number of areas made by a cross-section shape to create the volume. So in this case, let's just say, first of all, we're going to write the area of one square in terms of the given functions where we're going to have f of x minus g of x. Well, remember that the area of a square, of course, is side squared. And in this case, the side is given to you to be f of x minus g of x. So if we were going to write the area in terms of the functions, I would take that and I would substitute it in for s, and I would say that the area is going to be f of x minus g of x squared. And so they're not really giving us much space to write down here, so let's extend that. By adding an infinite number of squares, which is what I was kind of talking about, the total cross-sectional areas would wind up giving the volume created. So here, can we write what the integral would be for the volume? What integral would we use for the volume here in this case? Well, they're giving us our interval. So we're going to say the volume would be from A to B. And in this case, we're going to just take what we had here for the area. And in this case, I would say the area would be the integration of f of x minus g of x, or whatever the side happens to be, quantity squared dx. And that's how we would start using integration to be able to figure out what the volume is. Now, depending on what f of x and g of x are, we may be able to simplify that to one expression by combining any like terms that you might have. We may need to separate them and do the integration of f and then do the integration of g and then just take the difference of them. It kind of depends, but we'll see what we wind up with. Here we're looking at a what the cross-sectional region of a semicircle would look like for our two expressions for the f of x and g of x, where they're talking about those two kind of curves that are going to create the semicircular region. And here again, in this case, we're saying that this whole thing is going to represent the f of x minus g of x. That's representing the diameter. So that means that the radius would be half of f of x minus g of x. So the way that I would represent the area here, of course, the area of a semicircle is 1/2 pi times the radius squared. So if we do our substitution for the radius, I'm going to say, let's just kind of put it as over 2 here. Let's just say, let's see, 1/2 pi times, and we're going to have 1/2 time, and let's put this in brackets, 1/2 of f of x minus g of x, and that whole radius is squared. So that'll give us essentially, that'll give us 1/2 pi times 1/4 times f of x minus g of x squared. And overall, that's going to give us, in the numerator, we would just have pi times the radius f of x minus g of x squared, and in the denominator, the 4 and the 2 are going to combine to give me an 8. Or you could just say it as like 1/8 times all that stuff, or however you want to do it. And the stuff here at the bottom where it says write the volume generated by this. Okay, that's not going to be a terrible concept. What I'm going to do, looking at the expression that we have here, the pi over 8, that's just going to be a constant that can be pulled out. So here the volume will be pi over 8, pull out the constant, and we're integrating it on the same interval from a to b. So what's left over is essentially just the radius squared. So we'll say f of x minus g of x squared, as long as we're doing it, with respect to x, we'll say dx. If we were doing it horizontally to be perpendicular to the y-axis, we would say dy and all of that stuff. Here we got one more, a right isosceles triangle. In this case, this is where we're going to be looking at a 45, 45, 90 triangle, and it's a little hard to see, but it looks like the hypotenuse is kind of that diagonal to the right, where it's kind of sloping down diagonal to the right. I'm kind of looking at like that right there. That kind of looks like the hypotenuse to me. But again, in this case, we're looking here, they're giving us our 2 dimensions. F of x minus g of x for the 2 legs. So if I wanted to find the area here, it's just going to be, based on what we said a second ago, for a right isosceles triangle, it's going to be 1/2 side squared or side squared over 2, depending on how you wanted to think of it. And in this case, we're going to just plug in the value that they're giving us for the side. So here I would say the side is going to be 1/2 times f of x minus g of x squared, like that. Or you could write it as the f of x minus g of x squared over 2. And so the integration, the way that we would do that, again, I'm going to kind of take the 1/2. Let's go back to this color, I guess. We're going to take that 1/2 and we would pull it out as a constant. So the volume in this case would be 1/2 times the integration, and we're doing the same interval from a to b. And so we would just say the side squared, f of x minus g of x squared, and that's how we would find the expression for the volume. For an equilateral triangle, this one is going to, again, we saw that the area here for an equilateral triangle was either s squared times the square root of 3 over 4. That's how we were writing the area in this case. And so again, we're going to just kind of do our substitution for the side. And so I would wind up with, I think this one will be a bit easier if I kind of write the area as the square root of 3 over 4 times side squared, because of the expression that they're giving me. So with the expression that they're giving me, I'm going to wind up with the square root of 3 over 4 times f of x minus g of x squared. And again, taking that as our Q for the volume. Again, I'm going to take the radical 3 over 4 as a constant and pull that out of the integral. So I'm going to have the volume in this case would be the constant radical 3 over 4 multiplied by the integral from a to b, again, of the expression for the side here in this case, f of x minus g of x quantity squared dx. So hopefully you're getting an idea of what the cross-sectional shapes are going to look like, as we spread them out over a three-dimensional area. And from there, now that we've established how we can use an infinite sum of those areas to get the volume, now and establish how we can kind of take the area expressions and use them for our integration. Now it's time to put them into practice and see, can we actually find a volume in this case? In this example, find the volume of a solid whose base is bounded by the function y is equal to the square root of x and the line x equals 4 and the x-axis. So we have our curve for the square root of x. We have a vertical line at 4, and we, of course, y is equal to 0 for the x-axis. Each cross-section is a square. Okay, so the fact that they're telling us here it's a square, that kind of lets us know what formula that we're using. And it's perpendicular to the x-axis. Okay, so because it's perpendicular to the x-axis, that means we would basically, have everything solved in terms of y. Now, looking at this here, and it doesn't really matter where you do it, because it's going to be perpendicular to the x-axis, this is going to represent, we're looking at it kind of two-dimensionally, kind of head-on. This is going to represent the side of the square, which is going to be bounded by the square root of x. You can kind of imagine, I'm not a very good artist here, but you can kind of imagine that this would be the square root of x as it goes up, and then we would have kind of something going that way and something going this way, and it would just kind of repeat itself, where this is kind of like the x-axis, and of course the y-axis is kind of coming up this way with the curve, whatever that is, going that way. And there's our area. So in this case, the vertical segment that would represent the cross-sectional area is going to represent a side length for a square to be the square root of x units long. Because it doesn't matter where you do it, whether I start it kind of here, that vertical line is just going to be whatever the square root of x is. The same thing here, this vertical line is just going to be the square root of x. So all throughout that region where we're starting at 0 and going to 4, so this is going to be the interval for our integral from 0 to 4. Now we can recognize that because it's a square, the area of the square is side squared. Well, in this case, the side of the rectangle, the side of the square is whatever the square root of x happens to be. So if I wanted to do my integration, I'm going to take the area and say that the area is going to be the square root of x squared, which would just be x in this case. So when I do my integration now, I'm going to take my final area expression. Let's go to a different color for the integration. We're going to do our integration, so we're doing our volume here. We don't have any constants to pull out, but our interval, again, is from when x is 0 to when x is 4, x dx. And this one's a pretty easy thing to find the antiderivative of. This one would be a 1/2 x squared evaluated from 4 or from 0 to 4. Now the 0 really doesn't matter because when I substitute 0 into x squared, I'm going to wind up with 0, but I'll go ahead and write it out. So we have our constant 1/2 times 4 squared minus 0 squared. So here 4 squared is 16. 16 minus 0 is 0. Half of 16 says the volume would be 8 cubic units. And that's a pretty simple and straightforward example of how we're going to be using integration to, identify the volume of a region. But that's it. Are they going to get a little more complicated? Yeah, they're going to get more complicated. This was about as simple as you could make one, but here we have a circle. Now I know in your notes they don't give you the graph. You have to be able to know what the graph looks like. For time purposes, I'm just kind of providing a copy of what the graph looks like, but you really do need to make sure that you remember how to graph these things. Find the volume of a solid whose base is bounded by the circle with the indicated cross sections perpendicular to the x-axis. Okay, so perpendicular to the x-axis again means we want everything solved in terms of y. And it's telling us that we have isosceles right triangles with the hypotenuse lying on the base. Okay, so that one, if we go back a few slides, I don't know where it was. Go back a few slides. Oh, go up. Right here. Come on, take me there. Oh, I'm there. Ha ha ha. This is the one that we're kind of looking at potentially for the area of the triangle with the hypotenuse as the base. So let's go back to that example. There we go. So you can kind of imagine in this case that we kind of have a right triangle that's going to be kind of this way, right isosceles, where here's my right angle. And the base in this case, this is going to be that vertical distance, whatever y is, and this is going to be the vertical distance, whatever y is. So there's our cross-sectional area, and of course it's going to get bigger and smaller as you kind of, expand the dilate bigger or smaller the area of the triangle. So in this case, because I'm solving something in terms of y, that means I'm going to take this where it says solve it in terms of y. That's what we want to do. So let's see what we have for there. That would be y squared would be equal to x, nope, 9 minus x squared. That'll probably be the better way to write it, 9 minus x squared. And let's see what we have. I'm not thinking that we really need that area formula so much. I think that because they're giving us a formula for the triangle that we can solve it in terms of y, I think we should kind of be okay with that. But let's see. Let's go back and look at the area formula. In this case, let's see here, the area. Let me go to a different color. The area that we wound up getting was 1/4 b squared, or side squared as I think I had it written before. So let's just go ahead and write it as side squared. So I had it as 1/4 side squared, or I think I might have actually had it written as side squared over 4. So in this case, the side that we're going to be talking about, the way that we would kind of divide it, this would be y, of course, this would be y. Those would be the base and the height of the triangle that we're finding the area of. So the side in this case is just y. So I have my area to be y squared over 4. And let's see, is that it? What about area of a triangle by itself? 1/2 times the base times the height. Well, the base of the triangle here, the overall base of the triangle would be 2y. So 1/2, that would be 2y. And the height of the triangle is going to be 1y. And the 1/2 and the 2 are going to simplify, so I get area is going to just be y squared. So if area is y squared, then here I'm going to say the area is going to be 9 minus x squared. So this here didn't pan out like we wanted it to, but that's okay. Now, what is the interval of the volume? If you notice, in this case, the radius of the circle, either from the equation or from the graph itself, the radius of the circle is going to be 3, meaning that the interval is going to be from -3 to a +3 because it's centered at the origin. Now, what I would prefer to do, if it's possible, is I would prefer to have, just like what we saw in the last example, I would prefer to have one of my numbers to be 0, from something to 0 or from 0 to something. And in this case, I'm going to go from 0 to 3, like looking at it here, like if it's a semicircle, I'm going to be looking at it from 0 to 3, and then I'm going to just take that and double it. And that will give me the area of the entire thing from -3 to +3. We're just using the fact that a circle is going to be symmetrical here. So now that I know the area of the figure, and now that I know the area of the figure is going to be 9 minus x squared, and we have our interval for the integration. I'm going to say my volume in this case I'm going to double it, so that way I can go from 0 to 3, and we're going to use that integration of 9 minus x squared dx. So let's go ahead and start integrating here. And my volume here, we're going to say 2. The antiderivative of 9 is just going to be 9x. And then we'll say minus 1/3 x cubed. And we're evaluating it, in this case, from 0 to 3. And again, the reason why I want to have 0 is, you notice when we substitute 0 in both of those x's, they're going to just create 0. So we have here 2 times 9 times 3 cubed minus 1/3 times, nope, I put that cubed in the wrong spot, didn't I? Yeah, we're not cubing there. Minus 1/3 times 3 cubed, and then we'll say minus 9 times 0 minus 1/3 times 0 cubed. So all of this goes to 0, and I will have 2 times, so 9 and 3 gives me 27. 3 cubed is 27 over 3. That'll be minus 9. So that'll give me 27 minus 9 is 18. So double that, and I get a volume of 36 cubic units for my cross-sectional volume. Now, at any time, feel free to try and go ahead and pause the video and work any of these examples out on your own and see what you're able to wind up getting. Let R be the region bounded by the graphs of x is equal to y squared and x is equal to 9. Find the volume of the solid as R that has R as its base, and every cross-section plane is perpendicular to the x-axis as a semicircle. So again, perpendicular to the x-axis means that we're having everything solved in terms of y, and of course now we know the shape that we're looking at, so we're going to have something that has area is going to be half times pi times the radius squared. And let's see what we're going to be looking at here. In this case, they're saying R is the region bounded by the graphs. Find the volume such that R has the base. Okay, so in this case, the semicircular shape that we're going to be looking at here, where it says R, I'm going to say that Y is going to be the same thing as the R, the radius of the semicircle, because if we're doing a semicircle, just kind of imagine like this, and I didn't draw that very vertically, but imagine that is the semicircular shape that we have here, and we'll just, I guess, kind of put our little semicircle shape in there. Again, imagine, tilt that in your visually in your head, or go back and look at the example of what that would look like, spread out over multiple semicircular regions. Well, that would be the diameter. So in this case, the radius is just whatever this y value is and whatever this y value is. Now, of course, the y value at the bottom is negative, but think about it just in terms of the value, the distance. What is that length? It would just be whatever the length of y happens to be. And if we're solving this in terms of y, well, let's take the expression that we have and let's solve it in terms of y. So the expression that we got for the sideways parabola here is x is equal to y squared. So that means that in this case, we're going to get a positive negative square root of x to be equal to y. And that is how we're going to be able to start getting our area. So I'm going to take the area formula, and we're going to say, okay, well, the radius we've said was going to just be the y value up and down. So I'm going to say 1/2 times pi times y squared. And I'm going to take this positive or negative, and it doesn't really make a difference which one I substitute, but I'm going to substitute that in here for y. So my area expression will be 1/2 pi times the square root of x squared, which would just be x. So area in this case is going to be pi times x over 2, or 1/2 pi times x, however you want to think of it. But now that we have that, we are able to do our volume with our integration. So the integration in this case, for our volume, we're going to say, what are we integrating it to? The interval, because we're going perpendicular to the x-axis, we're doing everything vertical with respect to x. So we're starting here at 0 and we're going through 9. So that is going to be my interval from 0 to 9. And we have 1/2 pi x dx. Well, I'm going to take the 1/2 in pi and pull that out as a constant, 1/2 pi, or pi over 2 if you prefer, 0 to 9 of x dx. And now we can take the antiderivative here, so we have pi over 2. I'll just simplify that a little bit. And the antiderivative in this case is going to be 1/2 x squared evaluated from 0 to 9. And the 1/2 inside of those brackets, that can be pulled out as a constant, and that would give me pi over 4 times 9 squared minus 0 squared. So that'll be 81 pi over 4. There we go. And I think that is really the last example that we have where we're going to be looking at it in terms of, our standard derivative vertically with respect to x. The other examples that we have to take a look at, we will be taking a look at them with respect to y now. Find the volume of a solid whose base is the region bounded by the lines x plus 2y equals 6, x equals 0, and y equals 0. So the x and y axis, and we have a line that's written in standard form. Cross section takes perpendicular, so perpendicular to the y-axis. So perpendicular to the y-axis means, in this case, solved everything in terms of x. And it's giving us a shape here for equilateral triangles, so we kind of know what we're going to be looking at for the function. So the x equals 0 and y equals 0, those are just the y and x axis respectively. But let's take a look at what is this one going to be on our graph? And I know we want to solve it in terms of x, but I'm used to just doing these in terms of in slope-intercept form. So I'm going to look at that real quick. Let me see where I have some space. We have, let me maybe do this in a different color. We have x plus 2y equals 6, so we want to solve this in terms of x. So when I move the x term over, it's going to become negative divided by 2. That'll be negative 1/2 x plus 3. So we'll just, I don't know, say that here is my y-intercept of 0 and 3. And it's going to have a slope of negative 1/2. And I'm not really going to try and make it really super great. When y is 0, x is going to be 6. So maybe I should move that down a little bit because I kind of have them scaled equally almost. Let's do about here, 0 and 3, and this would be 6 and 0. And I'm just finding that by substituting 0 in for y to show that x is going to equal to 6. So here is the vertical line, and so that's essentially what we have, is we kind of have that triangular shape because we're looking, you know, for when x is equal to 0 and when y is equal to 0. Though that is the shape that we're going to be looking at. Now in this case, because we're doing it in terms of the y-axis, we're going to, let's try this yellow color here, see if that shows up okay. We're going to be, instead of doing a vertical cross section, now we're doing a horizontal cross section where that vertical length is going to be whatever x happens to be. Okay. So let's take our function or the equation that they gave us in terms of x, or let's take the line that they gave us, this line right here, and let's solve it in terms of x. So that would just be, you know, x is equal to 6 minus 2y. So that's going to be x, and in this case, because they're giving us equilateral triangles, the area of our equilateral triangle that we had was like the square root of 3 over 4 times side squared, and in this case the side of the equilateral triangle is going to be x, so that would be the square root of 3 over 4 x squared, like that. And because x is this, we're going to take that and put it in here. So that would be the square root of 3 over 4 times 6 minus 2y squared. So that is the that's going to represent the area, the cross-sectional area of the equilateral triangle horizontally based off of the y-axis. And here, in this case, we can go ahead and see what we're going to get for the volume. So let's get our volume expression going. And just like what we've seen in previous problems, the constant, the 3/4, I'm going to, or the radical 3 over 4, I'm going to pull that out. So we're going to say radical 3 over 4. And what is the what's the interval of my integration? Well, we're doing it with respect to the y-axis again. So this is at 0, 0. This is at 0, 3. So the interval in this case is going to be from when y is 0 to when y is 3. That's the interval that we're going to use for our integration. So that'll be 0 to 3 here. And let's see what we have. We're going to say 6 minus 2y quantity squared dy. If you want to, on this one, you could probably do u substitution, but because we only have the one expression, I'm going to go ahead and just expand it and treat it as a just a normal polynomial in standard form. Radical 3 over 4, 0 to 3, and if I expand that, I'm going to wind up with 36 minus 24y plus 4y squared dy. So now I will be able to take the antiderivative, and in this case I'm going to have the 3 radical 3 over 4 times, we have 36y, and then we're going to say half of 24, that'll give me minus 12y squared, and then a third of 4 is just going to be 4/3 plus 4/3 y cubed, evaluated from 0 to 3. And again, we're happy to have that 0 there because you can see when we substitute 0, everything is going to cancel out and create nothing. So I'm not, in this case, I'm not going to bother substituting the 0 simply because I don't have a lot of space going side to side. Just understand if you substitute the 0 for y, all 3 of those terms evaporate to nothing. So this will be radical 3 over 4 times 36 times 3 minus 12 times 3 squared plus 4/3 times 3 cubed. And I'm not going to lie, probably going to grab a calculator here. Radical 3 over 4. So 36 times 3, 8, carry the 9, 10, that'll be 108. And 9 times 12 will be a negative 108. Okay, so those are going to cancel. So 27 over 3 will be 9 times 4. That'll be 36. Hey, didn't need a calculator after all. So these are going to cancel. So I really just have radical 3 over 4, and the 4 goes into the 36 9 times, so that'll just work out to be a 9 radical 3. Not too shabby. Not bad. I thought I was going to have to grab a calculator there, but my brain worked it out. Go brain. It can do stuff from time to time. It's been known to work occasionally. The warranty's expired, but I don't get calls for brain warranties. Just car warranties are expiring. So anyway, here's our last example that we're going to take a look at for the cross-sectional volumes. Here it's again giving, let R be the region bounded by the graphs of y equals x squared and y equals 2 minus x squared. Find the volume of the region where the, and I believe in your notes, there's a typo. The presentation, or not in your notes, there's a typo in the presentation. The handout that is associated with this material is asking you to do it with respect to the y-axis again, not to the x-axis, and that's what it says in the presentation. It says x-axis, so I changed it so it would say y-axis. Now it tells us that, again, we're doing perpendicular to the y-axis, so because we're doing something perpendicular to the y-axis, we want things solved in terms of x instead of in terms of y. We're doing something with a rectangle where they're telling us that the height of the rectangle is going to be 3. Area of a rectangle is pretty straightforward. We're going to say area of a rectangle is just base times height. So in this case, it's just going to be 3 times whatever the base happens to be. And the base is going to be this when we take that and solve that in terms of x. So let's see what we get here. Let's see. Let's do that one in a different color. Let's take that expression. Let's take that expression and solve it in terms of x here. So we have y equals 2 minus x squared. So that'll be x squared equals 2 minus y. So x will be the square root of 2 minus y, and that's essentially what the base is going to be, because when we're doing, now let's get to the graph, because maybe that'll make it easy to see what I'm going to be substituting. Now should you be able to graph both of these? Absolutely. We have a quadratic parent function, right? Which is, we'll do the quadratic parent function here. And again, just a rough sketch. We have something like that, and that's not a very good sketch, but you get the idea. And this one here, let's do this one in green. Let's graph this guy here. It's shifted up 2 spaces and reflected vertically. So here's 2. It's going to be something like that. Now the sketch that I had is, it's not at all accurate. It's just that's what it should look like roughly. And this point of intersection and this point of intersection really should be the same. I didn't do a very good job of sketching the graph, but guess what? I cheated a little bit, and we got a little graph to help us with it if we need it. We got this guy right here. That's what they should look like when you graph them properly. But again, should you be able to graph a quadratic? Absolutely. At this point, yeah, you should be able to graph most functions without a graphing calculator. So in this case, here, let me try to pick a brighter color that's going to stand out on that background. Since we're doing it with respect to the y-axis, okay, so everything is going to be going this way, basically. Well, at this point here, where the 2 functions intersect, we're actually going to have 2 different boundaries. I'm going to have this boundary here on the bottom, which we can call A, and I'm going to have this boundary up at the top, which, you know, just for lack of a better word, we'll call it B. Okay? And the reason why we're separating those boundaries is because of the interval. Okay, so on the y-axis here, I'm at when y is equal to 0, and I'm going to go up to where y is equal to 1. So that's going to give me one interval from 0 to 1 that I have to integrate. But then I'm going to pick it back up, and I'm going to go from 1 up to here to this 2. So I'm going to have another interval from 1 to 2 that I need to integrate. So in this case, we're going to wind up with 2 regions that we're going to have to integrate in order to be able to get the volume the way it's supposed to be. So let's see what we have. We have something in terms of x, but that's only for 1. That's that y is equal to x squared. This is going to be the base, or the base of the rectangle for only one of the regions, because I wasn't thinking about it. We actually had 2 graphs here, so I need to solve that one in terms of x also. So let's go ahead and do that when we're going to have y equals x squared. So that means y would be equal to the positive negative square root of x. So this is going to be a base of the rectangle. This is going to be a base of the rectangle. We just need to make sure we know which one goes where. And in this case, the yellow one is going to kind of be at the bottom. So all of the x's here, this is going to be on the bottom. And all of the x's in the top portion, that's actually going to be kind of that pinkish color, okay? Because of the, you know, this is the transformed function. So all of the x values that we're going to be looking at are going to be based off of the transformed function. So all of this is going to be the base of the top portion, and this will be the base of the bottom portion. Okay, so let's see what we have here. And in this case, the x value, the base, actually the base of the figure is actually going to extend all the way across. So this is x and this is x. We actually have 2 of those that we're going to be looking at here. So the base in this case will actually be 2 radical x. Here, the base, that as we would go to the top, again, it's going to extend all the way across. This is x, so I have 2 of those. So here the base is going to be 2 of those 2 minus 2 times the square root of 2 minus y. And that's going to make up our regions. So this one here on the right, this one is going to be used for the interval from 1 to 2. And the one on the left, and that I have in yellow, that will be the base of the rectangle that we use on the interval from 0 to 1. So now that we know what the intervals are going to be, what the bases of each rectangle is going to be, now we need to start doing some integration here. Okay, so here I'm going to actually do my integration in 2 different colors, simply because we have 2 different regions that we're going to be looking at. So the volume in one case from 0 to 1 is going to be the area of the base, which is what we're looking at here. The area of the base is going to be that. So I'm going to say 3 times 2 radical x. I don't know what I was writing, but it sure wasn't an x. Radical x dx. Nope, nope, nope. That's y. Haha, y. Why did I solve that in terms of... What did I do? I totally messed up that yellow side, didn't I? I said it had to be in terms of x. We had to solve it for x. And what did I do? I solved it in terms of y. And somebody sitting at home or wherever you're watching this has been screaming at me saying, "No, you fool. This is not right." So let's go back and reevaluate that real quick. Glad I caught that mistake before I went too much further. But solve for x, so we had y is equal to x squared. So we square both sides, so that'll give me, or we take the square root of both sides, so that'll actually give me the square root of y, positive or negative, to be equal to x. And again, I have 2 of those. Oh, looks like it's time to go home. So the base in this case will be 2 of them. Right? Yeah, 2 of those, 2 radical y. So I have 2 x's, so that will be 2, yeah, there we go. Okay, now we're okay. So let me come back and erase this. So this will be 2, oop, I'm going to go back to my black color there. Black color. 2y dy. And we're going to add the integration from 1 to 2. And this one I got right. So we're going to say the area of the base. So we have 3 times the area of the base, which in this case would be 2 radical 2 minus y dy. So both of these in this case are going to produce a constant of 6. So I'm going to take this and pull it out here as a constant. Same thing here. Pull that out as a constant. So that'll be 6, 0 to 1, square root of y dy, plus 6 integrated from 1 to 2, square root of 2 minus y dy. Now this is where I can start doing the antiderivatives, and I'm going to do the antiderivatives in 2 different colors. The first one, let's just do that one in green, the one on the left. So here I'm going to wind up with 6 times, so that would be y to the 1/2. 1/2 plus 1 is 3 over 2, so that would be 2/3 y to the 3 over 2 power, evaluated from 0 to 1, and plus, and I guess this should be black. And let's do the other one in blue. Now this one here, when I do the integration on this one, I think it's going to be easier to do u substitution at this point. So for this one here, I'm going to say that the u term, nope, not y, I said u, but wrote a y. My brain and my hand don't want to communicate very well together today. So here we're going to say u would be the radicand 2 minus y minus y, so that means that du in this case is going to be just a negative dy, negative 1 times dy, and that doesn't match here. We got to get rid of that negative, so that'll be negative du to be equal to 1 dy. So there we go. Now we have things matching. So when y is equal to 1, what is u going to be? So 2 minus 1 would give me a 1 for u. And when y is equal to a 2, the upper bound, what would u be? So 2 minus 2 gives me u to be 0. And if we notice here, the upper and lower bound wound up switching. So let's see here. We have the 6, and we're going to, so just substituting directly, the lower bound gave me a u term to be 1, and the upper bound gave me a u term to be 0. And of course that is not really going to work out very well. Oh, and I got that negative sign there, so let's change this from a positive to a negative. So let's say minus 6. Hold on a second. Okay, sorry for the pause on that. A student came into my room and I need to help them out real quick. But let's see, getting back to where we were at. Let's see, let me just, reset a little bit here. We were talking about doing the u substitution for the upper bound or for the upper region of the graph that we were looking at. So we start off by incorporating the negative sign of the u substitution that we got, and if we substitute part for part of the integral, the lower bound for x gave me a lower bound for u of 1. The upper bound for x gave me an upper bound of 0 for u. And this is going to wind up being u to the 1/2 power du. And of course, when we reverse that, so let me give myself a little bit more space here. When we put the integral back in its proper order, the sign changes back to positive because we multiply with a negative 1. So this goes back to a positive 6 integration from 0 to 1 now, u to the 1/2 du. And now we can start taking the actual integration of each part. So since I have the blue, I'm going to go ahead and just finish this part here. So we say plus 6, antiderivative of u, 1/2, that'll be 2/3 u to the 3/2 power, integrated from 0 to 1. So the 0 I'm not going to bother worrying about, and 1 to the 2/3 power is just 1, so 2/3 of 6 is going to be a positive 4. All right, so let's go back and finish the integration of the other part in green. Let me get my equal sign here. So we've done the antiderivative, and again we have to do our substitution, and we actually had the same thing, it looks like. If I substitute the 0 in for y, it doesn't matter because it's going to make everything 0. So all I really need to do is substitute the 1, and 1 to the 3/2 power is just 1. 2/3 of 6 is going to be a 4. So 4 plus 4 gives me overall a region of a cross-sectional volume to be 8 cubic units. And that is going to wrap up the final example that we have for how we're going to use integration with cross-sectional areas. It's very similar to what we did with the, just everything that we do in calculus with a limit. We did it with derivatives to be able to find the instantaneous rate of change. We did it with integration to be able to find the area of the curve. And now we're doing it with integration to be able to find the volume, where we're just adding up an infinite number of cross-sectional areas to say this is what the limit of those cross sections are going to be to give me a volume. And that's it for this video. Hope that you were able to find some useful information out of it, and it is going to help you anytime that you need to perform a strategy like this. Just keep in mind, pay attention to where it's asking you to do the integration with respect to. Are you doing it perpendicular to the x-axis or the y-axis? Remember, if you do it perpendicular to the x-axis, you solve for y. Perpendicular to the y-axis, you solve for x. And pay attention to the shape of the cross-section that you're using. That's really the trickiest part, is making sure that you get the area correct. But until next time, ladies and gentlemen, thanks for watching. Take care and be good.